Hello. So, we are in the module 3 where we are discussing the two sample problems using the non-parametric tools. Now, we are almost on the verge of finishing out this module. This lecture will give you some flavor related to the extension of two sample problems. So, when I am saying two sample problems, our attention is restricted only between two populations, okay, whether these two populations are equal or not. But what happens if you are coming across with more than two populations, right, with say k population? How do you make a test to check whether these k populations are identical non-parametrically? Clear? So, this lecture will give you the extension of two sample problems. Extension to two sample test, k sample non-parametric test. The natural extension of two sample problem is the k sample problem, where k independent set of observations, one from each of the k continuous CDFs f1, f2, fk are taken over. So, 2 points to be remembered. One is the populations which are under our study, they are independent, and the second one is the all of the populations are assumed to be continuous. The null hypothesis as it is f1x is equal to f2x is equal to fkx, and the general alternative is simply that the populations differ in some way. The location model, see, when we are saying that k populations are different, this difference can be reasoned out in many ways. Okay? This difference can happen because of the location, this difference can happen because of the scale, so on and so forth. But here we are specifically taking that k populations are different by their location parameter. Clear? So, the location model for k sample problem is that the CDFs are fx minus theta 1, fx minus theta 2 and fx minus theta k. So, theta 1, theta 2, theta k, these are the location parameters for these respectively k populations. Frequently, theta 1, theta 2, theta k are taken as the median of this k populations. Then one of the format of the null hypothesis might be theta 1 is equal to theta 2 and that is equal to theta k. So, that is the null hypothesis, and the alternative hypothesis is at least one of the equality deflects, okay? At least theta I not equal to theta j for at least one pair I not equal to j. In classical statistics, this type of test generally categorized under the aegis of ANOVA or analysis of variance, and I am pretty sure that almost all of you are familiar with this name ANOVA, and in ANOVA the test statistic is the F test, but what are the necessary assumptions one has to take while performing, while executing ANOVA? The k populations are normal. This is the first and foremost assumption. One cannot avoid this assumption while performing ANOVA. And the second assumption, with the same variance, therefore, may differ only in location. That means they are all of the populations have the equal variance. That is one more assumptions to be taken while performing ANOVA. In fact, before processing ANOVA, one should always test for normality and equality of k class variances by Levin's test. If these two assumptions fall short, you have to take the aid of non-parametric techniques as an better alternative. For ordinal data, Also you can use non-parametric one-way ANOVA, non-parametric extension of equality of K populations. Non-parametric tests require no assumptions except of continuous population. That is the only assumption, and many a times I keep saying that for non-parametric, continuous population is the one and only one recipe one has to embed, right? There is nothing new in it. Now we begin K-sample non-parametric location problem. There are few relevant tests related to the K-sample non-parametric location problem, but here we are going to study Kruskal-Wallis test, the most widely used one-way non-parametric ANOVA test. Let us have one quick example so that you people will have the idea that when you need to apply non-parametric one-way ANOVA or more specifically Kruskal-Wallis test. Suppose the observations are collected independently from 3 independent age group in terms of daily social media consumption, pretty pragmatic example, and that consumption is measured in hour. Is there any difference in average time spent among the groups? Now, the groups are formed in terms of their age. You can see 3 types of ages, 3 types of group of ages we are taking here. One is the pretty young age 15 to 25 year, that is group 1. Group 2 is 25 to 40 years and group 3 is greater than 40 years. And for group 1 we have collected 6 observations, 8 hours, 8.5 hours. So, that means the first person falling in that group 15 to 25 years, he or she spends 8 hours a day in the social media like in Facebook, like in Twitter, etc. Okay. And group 2 comprises of only 4 observations, so is group 3, and you can see how the naming has been done in Kruskal-Wallis. Understanding the naming, understanding the notation is very important. So, when I am writing N1, that means first observation, first group. When I am writing N21, that means second group but first observation. That means when I am writing Nij, I stand for the subscript I stands for the group demarcation and the second subscript stands for the observation, particular jth observation from that particular ith group. Now, for this example, see the sample size is very small. Normality assumption that 3 of the groups are coming from, each 3 of them are following normal distribution, that will not be a valid one. We have to take the aid of non-parametric ANOVA. So, development of Kruskal-Wallis test, assume all the populations are continuous, combine capital N observations, means the total number of observations, into a single ordered sequence from smallest to largest and assign the ranks 1 to n to the sequence. Okay. So, capital N is your total observation and you are making the rank of all these observations. Of course, the first rank will be 1 and the largest value will receive the rank as capital N. Under null hypothesis, when K samples are from same population, adjacent ranks are well distributed among the K samples. Then total sum of ranks capital N into n plus 1 divided by 2, pretty easy, 1 plus 2 plus 3 till plus capital N. So, altogether what will be the sum of the ranks n into n plus 1 divided by 2 would be divided proportionally according to the sample size among the K samples. Hence, for the ith group which contains ni observations, the expected sum of ranks would be expected sum of ranks, that means the value multiplied by the probability. What is the probability here? Capital N is the total number of sample size, and out of that capital N, small ni is the sample size valid for the ith group. So, the proportion is like that, small ni divided by capital N. So, after the calculation, this would come as small ni into capital N plus 1 divided by 2, expected sum of ranks. It is very important to note expected sum of ranks, because we will see how the expected sum of ranks differ from the observed ranks. That is it. That is the logic behind the Kruskal-Wallis statistic. Now, if the actual sum of ranks, that is the observed sum of ranks, assigned to the elements in the ith sample is Ri, then the Kruskal-Wallis test statistic looks like this H, and as you can see, H is nothing but the sum of the squares of the deviations with some constant multiplied just to make the distribution into a known distribution. Otherwise, one can go with just summation Ri minus Ni into n plus 1 divided by 2 whole square, nothing wrong in it. But these 12 by n into n plus 1 as well as 1 by Ni, that is multiplied because to fall that H into the distribution of a known distribution, which is chi square. Clear? The approximate size alpha rejection region is H. We reject the null hypothesis if H, calculated H, greater than equal to chi square alpha k minus 1. So, what is the degrees of freedom of chi square? That will be k minus 1. If you have k populations to be checked on, then k minus 1 will be the degrees of freedom of the chi square. Remember, Kruskal-Wallis test is used to test the differences in medians of k groups, but this test does not directly consider the medians. Probably you noticed that when we are constructing the test statistic, we are not involving the medians in that construction. What we are doing? We are just taking Ri minus Ni into capital N plus 1 divided by 2. So, where is the median involved here? Median is not here. Rather, we are testing whether the mean ranks are the same across the groups. Capital Ri is the rank of the sum. So, the rationale is that if the distributions are similar, difference in mean ranks imply differences in medians. So, they are the synonymous, whether you are testing by medians or whether you are testing by the mean ranks, right. In practical situation, ties may occur in the observations. If ties occur within a column, that means within the same group, the value of H remains the same, but if the ties occurs across the columns, then you have to break the tie, that is in the way that is least conducive to rejection of H naught for a conservative test. So, this is the chi-square table. I think it will be beneficial for you if you have that idea how to look at the rejection point, critical point right from the chi-square table. We reject H naught if chi-square calculated greater than chi-square tabular. So, here you have seen that chi-square, and as a suffix you will see the probability or the area for the right tail. You see that here in this chi-square graph, towards the right tail probability is given, and at the extreme left of this table you will find the degrees of freedom, So, first stick to the degrees of freedom and then look at your alpha. If it is 0.05, that means that black portion, that dark portion is alpha, alpha is equal to 0.05. Now, just have a look from this column heads that which alpha for a specific value of degrees of freedom will give you the chi-square tabular value, and make a judgment from that chi-square tabular value as well as chi-square calculated value. That is how the chi-square table can be helpful in finding out the rejection region. Let us get back to this example. We have started by this example. There are 3 groups of age and mu 1 is equal to mu 2 is equal to mu 3. Let us say that mu I is the median of the ith group. Now, the calculation for Kruskal-Wallis is not very difficult, but it is lengthy. Okay? It is very mechanical, and you have to do the combined sample ranking, you have to make the rank sum of each of the group, and thereafter you can figure out age. It is not very difficult as I am saying, but it is really lengthy. Okay, let us have a quick look over how we can solve manually in case we are being asked. So, combined sample, just draw, there are 3 samples, combined sample will be 1, 2, 3, 4. What are the ranks? There are repetitive observation, 4 is the repeated observation. So, in this 4 we have to go for the tie breaking, and 4.5, 4.5 you will see the ranks are being adjusted, and simultaneously you have to write the group wise division, that is the first observation is coming from group 3, second observation which receives the rank 2 is coming from group 1, so on and so forth. Then you have to figure out R1, R2 and R3. Finally, just by replacing the value of R1, R2, R3 in the mathematical expression of age after a certain algebraic exercise, you can figure out age as 48. As age, we know that age follows chi-square with k minus degrees of freedom, and here k is 3. So, 3 minus 1. So, chi-square 2. You have to get to the chi-square table on the next slide. Chi-square 2 tabular is 5.991 at alpha is equal to 5% level of significance. As your calculated chi-square is less than 5.991, we accept the null hypothesis. What was the decision rule? Once again, if chi-square greater than chi-square tabular, we reject the null hypothesis, but it is less than, therefore, we accept the null hypothesis. Medians of the each group are equal. Clear? You can use R as well. Let me open the R window, because R will make your computational labor lesser. Okay. So, let me open R window. There are 3 groups, as we have seen, 3 groups as per the ages. So, first write out group 1, group 2, I am just running them out, group 3. Just to incite your interest, what you can do, you can draw the box plot. What will be the benefits of drawing the box plot? Because from the box plot you will have a visual idea that how the group means are differing from each other. So, let me draw the box plot. See, the box plots are here, and yeah, of course, we can see that medians are quite closer to each other, first group, second group and third group, right from the x-axis terminology, you can see 1, 2 and 3 medians are pretty close to each other. So, we have a faint idea, we might have a faint idea that probably after the testing process the null hypothesis may be accepted. Okay? So, that is what that intuition one can gather from the box plot. Okay. Now, Kruskal test is the syntax Kruskal dot test, and least means you are binding 3 groups, group 1, group 2, group 3, as group 1, group 2, group 3 are 3 groups. So, you have to use the syntax least. Okay. So, let me run that. And Kruskal, I mean it is it exactly matching with the manual calculation we have done 1.33 over there we received, and here by R we have received the calculated chi-square as 1.3518 and degrees of freedom is 2, and p-value, look at the p-value, whatever box plot has guided us, it is not incorrect in fact, because 0.5087 p-value is quite huge as compared with alpha 0.05. So, null hypothesis is going to be accepted. Let me get back to PPT once again, just to give you some idea of post hoc analysis. There is one more example we are trying to fathom out. 30 patients are taken to check reaction time of certain drug while consuming with water or alcohol or coffee. Is very pertinent example. Below is the table of the reaction time test if the medians of the times of reaction under different beverage are equal. Now, if the data is saved in any CSV file, in my case I have saved the data in Kruskal_data.csv. You know how to call out a data once it is stored in the CSV, okay, read.csv. And you can see I have jotted down the snapshot of R here. Let me get back to the original window of R to give you the better understanding. Example 2, we are talking about data 1, CSV file looks like that. You can see that ID means the number of observation, number of people under the scanner, and the reaction time of the certain drug when it is consumed with water, when it is consumed with coffee, and when it is consumed with alcohol. Alcohol is right down here. So, this is the concept of CSV file, and you can see one factor is there, and that factor is the drink. Drink is the factor. Why it is a one-way ANOVA? Drink is a one factor, single factor, and this factor has 3 levels: water, coffee and alcohol. So, that is why one-way ANOVA is necessary. Okay. So, data 1, and just for making it sure that what is the rank of all the observations. So, you can just make a rank run, and you see data 1 dollar reaction means I am trying to ranking the reaction observations ranking, and tie there might have some repetitive observations. So, you need to break the tie. So, ties dot method is equal to average. So, ranks are here you will see 1, 2, 3, 4, these are the ranks of the observations. And well, one more thing, you have to mention that drink is a factor. Just now I told you that one-way ANOVA you need to have one factor. So, what is the factor running here? That is drink, and drink is as dot factor, that is most essential. Until or unless you run this syntax, it will not give you that structure of one-way ANOVA, right. Now, we can make a summary for when that drink is by coffee, level coffee, by water or by alcohol. So, if I just go for that data 1 and if I write here T, do you understand that what is 0.98, 1.11, 1.27? These are the reaction time while you are consuming that drug by the coffee. Okay, that's only coffee part is extracted. R is extracting only the coffee part right from the CSV file. Right from the CSV file, only coffee part is extracted. Clear? Finally, you can go for the Kruskal test, Kruskal dot test. So, Kruskal values chi-square is 16.322 degrees of freedom. Quite obviously, DF means degrees of freedom. Quite obviously, it turns to be 2 because there are 3 groups. And look at the p-value. P-value is extremely small, 0.0002, which is very small in comparison with 0.05. So, we reject the null hypothesis that the median reaction time for water, for coffee and for alcohol, they are not same. Okay. Let us get back to the PPT once again. After Kruskal-Wallis test, there is one type of test to be expected to be done, that is the post hoc analysis. Post hoc analysis, what is post hoc analysis? In my earlier lecture, I told you post hoc analysis means now you need to see which pair is different. When you are saying that H naught, the null hypothesis is rejected, that means mu1, if mu1 is the median of the first group, mu2 be the median of the second group and mu3 be the median of the third group, they are different. But which equality turns to be the inequality? Is mu1 not equal to mu2? Is mu2 not equal to mu3? Or is mu1 not equal to mu3? This type of 3 possible ways one can think of. So, Dunn test is the appropriate non-parametric test for such pairwise multiple comparison. If p-value in pairwise comparison by Dunn test is smaller than the significance level, then the null hypothesis that there is no difference. Okay, so, we are taking 2, that is first group and second group. Are they same in terms of the median? If your p-value is greater than 0.05, then you can say that there is no difference. If your p-value is bigger than 0.05, then you can say that they are identical. Okay. So, using R, we can perform Dunn test using the package Dunn.test. So, for this post hoc analysis, you have to install the package Dunn test. Let me get back to the R console once again to check on the Dunn test. Checking the pairwise comparison, library, first library, Dunn test. Now, Dunn test would be done on the data 1 reaction time and the factor is drink. That is how you have to write. The most interesting part of Dunn test is you can see the entire output along with the Kruskal-Wallis statistic. Already we have done the Kruskal-Wallis 16.3217 degrees of freedom 2 and p-value is very small, but here Dunn test is not giving you the exact p-value which you have obtained while dealing with just the Kruskal.test syntax. Now, in Dunn test that post hoc analysis is here, column row, column mean, row mean, coffee and water. So, coffee and alcohol, the test statistic is 1.94, whether coffee median is same as the alcohol median generally done test is similar to the Mann-Whitney test, and the test statistics is 1.943318 and the p value is 0.0260. They are not same. Similarly, water and alcohol, you see that for water and alcohol test, the median turns to be 0.0000. It is extremely significant. That is why that star appears, extremely significant. So, if you strict to less than 0.05, then the median for water level is not at all equal to the median for alcohol. Similarly, for water and coffee, here also you will find that star. Clear? So, alpha is taken as 0.05, reject H if p is less than equal to alpha by 2. Here all I am saying 0.05, but when you are checking, alpha should be divided by 2, 0.05 divided by 2. Even though 0.02 is less than 0.05, you have to make the comparison with alpha by 2. Clear? Alpha is 0.05 divided by 2, which turns to be 0.025. 0.025 is bigger than 0.026, then you may accept the hypothesis that coffee and alcohols are almost the same, the medians are almost the same. So, that is one point not to be missed. When you are performing done test, you have to check the alpha, not its actual value, but its half of the value. Okay, coffee alcohol and alcohol coffee, that is why half of the value alpha by 2, 0.05 divided by 2. Let us get back to the PPT presentations. Whatever I just now discussed, everything I tried to write out on this screenshot of the done test, just give it a look for better understanding, and this will be clearer to you. That is the Kruskal-Wallis test, and as I told you, Kruskal-Wallis test is the one-way non-parametric ANOVA. So, mostly Kruskal-Wallis test is used when you have the group type data. Just now we have seen that example. Thank you.